This section is just about using everything that we've learned so far to help us graph functions. So you've no doubt in algebra classes figured out how to graph functions, but you didn't have the techniques of derivatives and second derivatives to help you talk about the slope of the graph or concavity or points of interest such as maximum, local maxes, and local mins, that type of thing. So now that we have all that under our belt, we're gonna put it all together and be able to get a good picture of what a graph looks like without actually needing a graphing calculator. So there are several things that we're gonna get, and I'll give you the list here. I'm gonna do one example list, but use this list as a guideline for graphing functions that you do while you're practicing. Okay, so the first thing we want to do is identify the domain or interval of interest. So for this function here, which is 2x squared over x squared minus 1, the interval of interest is, or the domain, so the interval is really negative infinity to infinity, but we have to kick out plus or minus 1 because those are not in our domain. So I can identify that pretty quick. Let me use the right tool here. So I want everything from negative infinity to negative 1 unioned with negative 1 to 1 union with 1 to infinity. All right, now I want to find the intercepts. So that is the x-intercepts and the y-intercept. So let me write my function up here. Y equals 2x squared all over x squared minus 1. Now, if I want to figure out where the y-intercept is, that means set x equal to 0. All right, if I set x equals to 0, that means y is going to be 0. So my y-intercept is going to be 0 over 0. Now, of course, if I want to figure out the x-intercept, I'm setting y equal to 0. So I have 0 equals 2x squared over x squared minus 1. But of course, the only way for that to happen is if the x up here is 0, which we already know is going to be an x-intercept. So that is to say, my x-intercept and my y-intercept in this graph are going to be 0, 0. So in general, you want to find all the x-intercepts and y-intercepts. Okay, so that was step 2. Step 3, I'm going to use the symmetry of even and odd functions. So if you remember, an even function is where if you plug in a negative x, you get the same thing, same y value as if you had plugged in the regular x. So in other words, it's symmetric about the y-axis. An odd function, on the other hand, if you plug in a negative x, you get the negative y value as if you plugged in a positive x. So in other words, let me draw a crude graph here. An even function would be the same, kind of a mirror image on the left and the right side of the y-axis. An odd function has rotational symmetry. So you're looking at graphs that do something like this. So if you rotate it 180 degrees, you'd have the same graph. Okay, so in this case, you could ask yourself, do I have an even or odd function? Well, if I plug in x, I get 2x squared over x squared minus 1. If I plug in negative x, though, since I have an x squared here, that negative is going to become positive, so I'll still have 2x squared on the top. And on the bottom, that negative x gets squared, so that negative becomes positive anyway, so I get x squared minus 1. So I indeed have an even function. So I really only have to look at graph the right side, and the left side then will be the same. So I'm only going to look at I'm only going to graph 0 to infinity and try to figure out what happens there. Now, just for, I don't know, just for explanation, I guess, I won't actually use the symmetry, but I could. So I'll look for, this will be symmetrical. I guess we'll use that to verify that I've got the right graph. But, you know, if I come up with a negative critical point, then I'll still graph it just for the fullness of explanation. So I'm going to locate the vertical and horizontal asymptotes and determine the end behavior. So how we do that, well, vertical asymptotes are just anywhere where my function is not defined. So, which isn't entirely true, but the idea is that in this case, at -1 and 1, because this is a rational function, I'm going to have vertical asymptotes there because they would, -1 and 1 plugged into my function would give me a 0 in the denominator. Okay, so I've got vertical asymptotes there. Maybe I can draw that a little nicer. Well, there's -1, and here we are at 1. There's my vertical asymptotes. Alright, so now, do I have any horizontal asymptotes? Well, to figure that out, we can divide both sides, divide top and bottom of our function by x squared, because really what I'm looking for is, let me not say equals here, I want to know what happens as x goes out to infinity or negative infinity. So I guess here's where I'll use some symmetry. I'm just going to look at the x going to infinity, knowing that negative infinity will be the mirror image. As x goes to infinity of 2x squared over x squared minus 1, well, the easiest way to deal with this with a rational function is divide everything by the biggest power in the denominator, and that is going to give me limit x goes to infinity of 2 over 1 minus 1 over x squared, and of course that is going to go to 0, so this limit is 2. So now that tells me I've got a horizontal asymptote at 2. Let me pick one of these to be 2. I've got some horizontal asymptote at 2. So I've got to figure out what happens with the rest of this function. Alright, so end behavior, that means, you know, what happens as we go to infinity and negative infinity, looks like my function is going to be approaching 2 as I go to the right and 2 as I go to the left. Okay, so now we're on step 5. Let's figure out the first and second derivative. First derivative, so I can see where my critical points might be. Second derivative, so I can look at concavity of all this. Okay, so first derivative is, well, let's quotient rule this. Got x squared minus 1 times derivative of the top is going to be 4x, and then minus 2x squared times derivative of the bottom, which is 2x all over low squared. X squared minus 1 squared, and that's going to be, well, let's see, notice once I move this, distribute this in, I get a 4x cubed. I'm also going to get a minus 4x cubed from the second part, so those are going to cancel out. I'm going to have a minus 4x on top over x squared minus 1 squared on bottom. Alright, let's look at the second derivative. I'm going to come down here and make some, so I have some space. Hopefully I'm not interfering with where my graph is going to go. So again, let's quotient rule this. I'm going to have x squared minus 1 squared times negative 4 minus negative 4x times the derivative of the top, which is going to be 2 times 2x. That's not entirely true, is it? I'm not giving myself enough space. I'm trying to squeeze it in here. Let's say 2 times x squared minus 1 times, you're not going to let me write out here. All right. Let's move it. So that's 2 times x squared minus 1 times the derivative of the inside, which is 2x, all over x squared minus 1 squared squared, or to the fourth. So, well, let me come back to the second derivative, but let me point out that we don't really care about this denominator because it's always positive. And the thing we're going to get from the second derivative is the concavity. So we really only care where it's positive or negative. So let me simplify the top a little bit, and that'll help us figure out where it's going to be positive or negative. That's going to be negative 4 times something that's always positive. So in other words, this first part will always be negative because I've got negative 4 times a positive number. And then over here, let's see if I can simplify this at all. I've got plus 16 x squared times x squared minus 1. All right. And then, of course, over x squared minus 1 to the fourth power. Okay, so now what do we do with all that? Well, we can figure out where the intervals of increase and decrease are based on the first derivative. So where's the first derivative? 0. Well, that's going to be when x is 0. So a critical point is where my first derivative is 0 and where it's undefined. So 0, it's undefined at plus 1 and minus 1. All right, so that is at these asymptotes, the vertical asymptotes. Once I pass over those, I might switch from being negative increase to a decrease to an increase. So that's why I'm interested in those critical points. 0 is also another candidate. All right, so what I can do, since my graph is already split up though in those ways, I can plug these critical points in and see what kind of second derivative I get. So f double prime of x, let's go 0 first. Now what do you get? On the bottom, of course, you get a positive. Here you get negative 4 times a positive number. So I'm going to positive in parentheses here. So the whole thing is negative plus, I might have to be a little more careful here. Yeah, let's be a little more careful. So I've got negative 4 times 0 minus 1 squared plus 16 times 0 times negative 1. All right, of course that's 0, so this gets me, I'm just going to call it a negative number. So that means when I plug 0 in, I'm concave down. So my interval, my change of increase must be something like this at 0. So I've got an upside down parabola type shape. It's not a parabola, but it's that general shape. All right, so something like that in here. And of course I know my intercept is 0, 0. So that's why I want my y-intercept. So I know I'm going to do something like this, and as this graph goes down, I'll be getting closer and closer to infinity. So let me erase my sketch up top. So I've got part of my graph drawn. Okay, so then what happens, what's my second derivative if I plug in, let's stay on the right side. And we can use symmetry again if we want to. If I plug 1 in, well, now x squared minus 1 is going to be 0. So I've got 0 plus 0 over, 0. Well, that's not good. Okay, well, the reason we're getting that is because we're trying to plug in a number that is not in our domain. Okay, so we have to be a little more careful. Let's go back to the first derivative. Now, the only place where my function could change concavity, let me double check this here, but would be where my second derivative is 0. So let's check that. And I'm skipping ahead to number 8 here by doing this. So there's no reason you have to go in order of these steps, but they'll all help us graph, and so it might help us answer some of the other questions. So if I plug in 0 for my second derivative and figure out where the numerator is 0, that shouldn't be too hard. So notice I'm ignoring the new denominator because that won't make the function 0 at all. 16x squared is x squared minus 1. All right, well, let's see. I can divide everything by 4, first of all, and then algebra this. So I'm going to have minus x to the 4th minus 2x squared plus 1 plus 4 rather. I divided by 4. Be careful when you skip steps. Minus 4x squared. So simplifying this gets me 3x to the 4th minus 2x squared minus 1. And that, if we're lucky, is going to factor. So that factors into 3x squared plus 1 times x squared minus 1. Okay. So we can solve x squared equals 1, but of course that gives us our asymptotes. So that might be where our concavity changes. We'll have to be careful of that. But the other possibility is that x squared equals negative 1 over 3 from the first factor. Of course, that can't happen because x squared can't be a negative number. So in other words, there's nowhere that we're going to change concavity other than possibly over those asymptotes. So in other words, I've got a negative concavity in here, inside, between the asymptotes, but outside, I just have to figure out what that concavity looks like, and then it'll stay that concavity the whole time. And I know that my function will approach 2, so it's probably going to do something like this or like this as I go out to infinity. So let me just plug in one number that's outside of 1, so like, say, 2, and get the concavity there. Concavity 2, let's see. So my second derivative is here. I just need positive and negatives plugged in there, and really only into the top because I know the bottom is positive always. So I'm plugging in positive 2 into my second derivative, and I'm being a little loose here because I really just need positive or negative. If I plug 2 into, let's look at the simplified version right here. If I plug 2 into here, I'm going to get negative 4 times positive numbers. We know that's always positive, but I need to be a little more careful. I'm really trying to cut some corners here. but I shouldn't. This is going to be 4 minus 1 squared, and then plus 16 times 2 squared times 4 minus 1. So this is positive, this is negative, but is one bigger than the other is the question. Well, of course we get negative 12 here, and you're going to get 16 times something positive here, so that's got to be greater than 0. So that means my concavity is positive, which means that my function must be doing something like this. And getting close to 2 as we go further. All right, and then by symmetry, we must be doing something like this on the other side. Okay. So now, let's see, let's find the local maximum and min values. Well, for those, we just have to look at our critical points. But of course, 1 and negative 1 can't be max and min values. So we have to look at 0. It's the only place we might have a local max or a local min. And indeed, you can see from the graph, but you can also see from using our one extrema theorem. We only had one extrema in the interval negative 1 to 1, and we knew that the second derivative was negative, so it's concave down, which means that has to be a local max. So we have a local max at, or our local max is 0, the y value, at x equals 0, the x value. Okay, so there's a lot in here, but try using these steps, and again, not necessarily in the order that you see them, but try using these steps to figure out what a graph looks like, and then go to Desmos and double check that you're able to graph it.